Hello and welcome everyone. Thank you for joining us today. I'm happy to see there's a large number of attendees on the line, and we're honored that you were able to clear your schedules for this event. My name is Kara and I'm with the AIMMS marketing team, and I'll be your host. Today's webinar is on an overview of ODH CPLEX solver in the AIMMS platform. Both Alkis, Robert, and Mohan will offer a general review of the AIMMS Prescriptive Analytics Platform, as well as a dive into problems that might benefit from using ODH CPLEX, computational examples, as well as a demo of a use case running ODH CPLEX. Just a little housekeeping before we get started. Today's webinar will be about 45 minutes long, and your lines will be muted during the entire webinar. If you have any questions during the presentation, please type them into the question box in your control panel. NSK will take note of them and bring them up at the end of the presentation. You may also hold on to them to the end yourself, and we will process as many questions as time allows.
Not yet. Hey, good morning and good afternoon and good evening, everyone, from wherever you're joining. We appreciate you joining us today. It is my pleasure to welcome our speakers for today. So without much ado, let me start with Robert Ashford. Dr. Ashford, he has a master's degree in mathematics from Cambridge University and a PhD from Warwick Business School. He's authored over 20 academic papers related to optimization. He co-founded Dash Optimization in 1984, helped pioneer the development of new modeling and solution technologies. And when after Dash was sold in 2008, Robert continued leading development within Fair Isaac until the fall of 2010. Until he co-founded Optimization Direct in 2014. So welcome, Dr. Ashford.
Thank you.
Along with him is Dr. Alkis Vazakopoulos, which I am sure I'm butchering the name. I apologize for that. But Dr. Vazakopoulos is a pioneer in using parallel programming for solving large-scale optimization problems for several industry verticals, particularly as it relates to banking and retail industries. Dr. Vazakopoulos is a business analytics and optimization expert from Jan 2008 to Jan 2011. He was vice president at FICO Research, and prior to that, he was president at Dash Optimization, where he worked closely with end users, consulting companies, OEMs, and ISVs, and we're proud to welcome him to this webinar as well today. And joining both of them will be our own Mohan, who is part of our AIMMS user support group. He works very closely with our customers, helping them implement optimization solutions within AIMMS. He has a master's degree in industrial engineering from Penn State University. And last but not the least, he's a very close colleague of mine, helping me in my customer pursuits. So welcome to all three of you. Without much ado, I'm going to hand it off to them to take you to the meat of the presentation.
Okay, great. I would like to thank AIMMS for giving us the opportunity to present at the Welcome Series. And I would like to thank you for finding the time today to join us. So today, Robert, Dr. Ashford is going to talk about ODH. We're going to start with, giving you some background, our experience with large-scale optimization and what are the challenges. He's going to talk about the ODH heuristics approach, give you a little background and info about ODH heuristics engine. And then we're going to go to the ODH CPLEX optimizer. We are at release 5, so we're going to talk about new features in release 5. And then we're going to talk about practical and also some public benchmarks for in the areas of scheduling, supply chain, telecoms, and other benchmarks examples. And also, as I said, we're going to talk about public. He's going to give you some benchmark results for MIPLib models. Now, Optimization Direct, we work very closely with AIMMS. So our philosophy is to develop new approaches for optimization, difficult problems. Thus, we have developed ODH. We work with our software partners to develop new optimization techniques. We also provide the consultancy to solve complex business problems. And also we are getting into how we combine machine learning and optimization. We are going to have, talks about this in 2021. So stay tuned. This is a topic that we're working and we'll get back to you. So now I'll give, to Robert, and he's going to talk about the ODH.
Thank you, Alkis. I'd like to start by reiterating, I suppose, what many of you know, that is that when optimization is applied to very large problems or even mid-size problems, things can become quite hard. Now, many of you will be aware that models are becoming progressively larger and more complicated for a variety of reasons, not just for personal preference, but because larger models are often much more useful. When coming to look at those models, it's frequently the case that standard MIP technology gets either very stretched or it simply fails altogether. And most people, I think, are aware that the time to solve problems goes up superlinearly with their size. However, the reality is actually worse than that. And to illustrate this, I've taken a few hundred sub-models of a much larger scheduling model to show you how the time to solve them varies according to their size. So on the x-axis here, I've plotted the size of the model as characterized by the number of integers in it, and on the y-axis, the time to solve them to the normal optimality gap, imposing a time limit of 2 hours or 7,200 seconds. Now, as you can see, when the models are small, they all solve pretty quickly. In fact, you can't really see the time to solve moving much above 0. However, there was one model there at about 11,000 integers, I suppose, which timed out. As you can see, little spot there goes above the 7,000 line. Then the other models are all fine until we get to maybe 20,000, 22,000 entities, something like that. Then, hey presto, many of them start timing out. You can think of this almost as a kind of a wall, the barrier to actually solving optimization problems being a function of size. Everything's fine until suddenly we hit some critical size when the time to solve starts going through the roof. So what do we do about very large models? This is where ODH can actually help. Well, what is it? It's a set of tools for dealing with these very large and possibly difficult integer programming problems that exploits parallel hardware as much as we can. And this is now commonplace on most people's laptops, servers, and obviously workstations. The idea is to say something useful about these models, ideally producing good solutions. The tool itself uses IBM's iLog CPLEX solver for doing basic solution tasks, mostly for solving submodels. Now, the tools are captured in the main in what I call a heuristics engine, which can be used on its own to find good solutions to these very large models, but it doesn't give you any idea of actually how good those solutions are. In other words, it doesn't give an optimality guarantee, typically characterized by the gap, MIP gap, in traditional MIP solver software. That is to say, the gap between the solution you've got and what you know might be the best solution available. However, the OD heuristics engine can be run within the CPLEX optimizer with our ODH CPLEX product, using essentially CPLEX to do the main or master solve, and using the heuristics engine to provide solutions. That way we get the good solutions and we get an optimality guarantee, so we know how good those solutions are in the traditional way. And you can think of ODH CPLEX just as being another optimizer. It behaves very much like it. You can use it like it. But the objective of the optimizer is to provide good solutions to very hard problems, not necessarily to be able to solve much smaller problems as quickly as possible. The product itself, this is to general customers here, is sold as a software library, which is suitable for embedding in your own products. And I supply driver programs as for using it with command line, say, and skeleton scripts for compiling and linking them. Comes with a short user guide. This is not so relevant for AIMMS customers because the good folks at AIMMS have done all that for you and embedded the product within AIMMS itself. So you need to worry about that. You just treat it as an ordinary but different optimizer within AIMMS. Well, people ask, how does it work? Well, the idea is that we have some method of finding some kind of integer feasible solution. That is to say, a solution which is satisfying our integrality conditions and our constraints, not necessarily a very good one. And having found that, we try and improve it. So we attempt to find the solution by using our own bespoke local search techniques and using what the older members of the audience might recognize as being big M or phase one methods to try and get an initial solution by driving away those integer infeasibilities. Or indeed, you can just run CPLEX, and CPLEX may give you a start. When you're using ODH CPLEX, all these things happen at the same time. Anyway, once we've got a solution, we can then set about improving it. And we do that by decomposing the big model into lots of small submodels and solving the submodels separately. Combining the solution from the submodels into a solution for the whole model, and then repeating the decomposition. This process repeats, as it were, progressively increasing the submodel size. So typically, then we get a rapid improvement to the solution value at the outset, and that rate of improvement tails off as the submodel size increases and it becomes harder and harder to find better solutions. Now, the decomposition itself can be inferred from simple things like variable names. If you give it the product some kind of pattern to match. Or it can be done using a callback inside the software. And in fact, that's employed by AIMMS so that you can specify as an AIMMS user the decomposition you want to use from the structure of your model. And we'll see that later on. Or you say, oh, I can't bother with doing this, in which case ODH will infer a decomposition itself from looking at the matrix structure. As with most parallel optimization codes, you can run it in deterministic mode where it should give you the same result if you run it twice, or in opportunistic mode when we don't bother trying to synchronize the threads. And if you run it twice, you may get slightly different answers in different times. Most of our users probably use it in deterministic mode, but those with the largest and most demanding models frequently choose to run in opportunistic mode where you don't bother, as I say, trying to do any scheduling, so you save time doing that, and you get the maximum possible performance from your hardware. ODH has been around for some years now, and it's constantly under development, like CPLEX and the other MIT codes. It improves, hopefully, year by year. And over the first couple of years, it has improved considerably, possibly going, at least on workstations at least, 20% faster than it did 18 months ago. Now, some of this gain is achieved from using more recent versions of CPLEX, which themselves go faster. And some of it is obtained by changes to the ODH algorithm. Some of the changes I've highlighted there. We support so-called dirty solutions now, and we've improved the thread synchronization process to an extent that it now works quite well with hyperthreading or symmetric multi-threading, whatever you wish to call it, using, say, 8 threads on a typical 4-core laptop or workstation processor. And we've improved things like the management of submodels, trying to figure out how far to go before stopping, that sort of thing, which overall improves the performance considerably. We've made the product better to use by providing that user-specified decomposition callback that I mentioned earlier, and we have improved support for more exotic forms of integer object, like special ordered sets, indicators, and lazy constraints. For those of you who want to go off-piste, as it were, and use the product in a different environment, maybe from Python, we support the Python 3 and IBM's ODH CPLEX product for building models. And if you really want, you can use MATLAB and that sort of thing. We have improved recently the thread synchronization under Java, particularly under Linux, and many of our big users tend to use our software on servers, and typically these run Linux rather than Windows 2012. And Java is quite often the kind of modeling, building model management environment system of choice. Okay, to show that our software actually works, I've selected 7 models from real users that have come our way. These are quite hard MIPS, varying in hardness or difficulty, I suppose, starting with an easy one and going up to a huge one. And they come from 3 different application areas. The scheduling problems come from one of our big scheduling customers who, in the main, schedules satellites, actually, and comms around satellites. 2 of them are supply chain models from a supply chain modeling vendor, and the 3rd one's a huge. It's an optical network design problem from the telecoms industry. And you can see there the number of integer objects in these models varies from a mere 57,000 through to, what have we got there, nearly 13 million for the telecoms model. And that, in the main, it's the number of integer objects which determines how difficult the thing is to solve, with a possible exception there of the scheduling problem labeled phase 1, which is inherently difficult. It's hard to find solutions. So, although it's small, it's a problem that traditional optimizers find particularly tough as we move on to the next slide. Okay, here's how we get on using an ordinary 4-core Intel i7, which is in my workstations, and using hyperthreading to effectively run 8 threads. The easy problem solves, but it actually solves better with CPLEX. As you can see, the CPLEX does it in under an hour, and ODH CPLEX takes almost 5 hours. Well, not so good, but as the problem size increases, then ODH tends to perform relatively better. Although I should say that with respect to the easy model, it takes CPLEX maybe 15-20 minutes to find the optimal solution, whereas ODH finds it in 110 seconds, I think, if memory serves me correctly. But it takes ODH a long time to prove it compared to CPLEX. Moving on to the supply chain model, which I call mixed, we get a similar kind of story. And this time I said, okay, well, how long does it take to get to 1% gap? How long does it take to get a solution which we know is in 1% of any better solution that exists? Well, in the case of ODH, it only took 14 minutes as opposed to over half an hour with CPLEX. run for 8 hours, which I set to be the time limit. The results are broadly similar, although ODH, as you can see, got a better solution, one that's, I think, 0.0015 away from the percent away from best optimality. So not quite closing the gap, but very, very close to it. For the medium-sized scheduling problem, you can see there that run for 8 hours, ODH got a better solution, although you might say that the 37% gap solution is not brilliant. In fact, the user tends to run for a day or so on this model to get a much better solution. CPLEX, on the other hand, get a very relatively poor solution within that 8-hour time frame. Moving up to the difficult scheduling problem, you can see that CPLEX failed to get a solution at all in 8 hours, whereas at least ODH CPLEX got some solution, albeit not a very good one. The user, again, in this instance, tends to run for much longer than 8 hours to get solutions with a better optimality guarantee. The large supply chain model was kind of an interesting one here. ODH managed to get a very good solution in 8 hours compared to a much poorer solution than traditional MIP. And the story with the smaller but tough scheduling problem in phase 1 is that we get a pretty good solution in 8 hours using ODH CPLEX, one that's down to the accuracy of the data that's used in the model, and no solution at all from traditional MIP. The story for the huge telecoms model is that neither technology does particularly well, although both get a solution and ODH does slightly better. We can see how the results shake out using, say, 12 threads on a server in the next slide. Okay, similar story. This time, ODH happens to beat CPLEX on the easy model, but you've got a similar story there with the others. If you want me at the end to go back over any of these slides to discuss particular numbers, I'm happy to do so. But for the moment, to avoid people suffering from number poisoning, we'll move straight on to the next slide. And a lot more problems. This time, I've taken a wider range of problems. You can see the first 3 of them there come from AIMMS customers, and use technology for 2 hours into the problems to see how we get on. They are of significant difficulty, all of them, although you may think, well, some of them don't have all that many integer entities. RPRS, for example, has fewer than 50,000 binaries, which is perhaps not that big. But they are all quite hard. And we have examples from other industries on the next slide. Forestry, interestingly enough, has been a traditional area for optimization. When I started my career back in the late 1970s, we were solving huge LPs posed essentially by US forestry. These forestry management LPs, MIPs here, come from a forestry systems or management systems vendor and are amongst the most difficult, I think, that I've ever seen. And they're pretty big, as you can see. The bigger the model there, the more detailed it is. You're not quite able to characterize each individual tree, but the forest can be divided up into smaller and more equitable areas. We have a model there from telecoms field installation. Interestingly, we have a number of models from the healthcare sector where we're doing things like scheduling operating theaters. We have another standard telecoms model and 2 models from electrical power generation. Let's see how we get on. Okay, with 8 threads on a 4-core workstation, you can see that ODH CPLEX performs on average significantly better than the standard MIP technology using the CPLEX 12.10. In numbers in green there represent where ODH is performing better than the standard technology, and the ones in red where it isn't. So it tends to perform relatively less well on those easier models, ones where we get to a 0% gap, in other words, terminate relatively quickly. On the big models, it tends to win all the time. On the small models, sometimes it doesn't. As you'll see, the other results are on the next slide. Okay, and again, we've got it doing relatively better on the bigger models. So, gaps like 8% represent possibly usable solutions, whereas gaps of maybe 16% represent solutions that are considerably less usable. On the next slide, we can see how they maybe shake up using more threads. And it's a similar story. I mean, there's some element of luck involved in solving all these models, of course. So there'll be some minor variations. It happens that CPLEX does pretty well using 12 threads on that little RS model, whereas it didn't using only 8. Okay, we've got a similar story here on the other models with, on average, much better performance in using ODH CPLEX. By measuring performance here, perhaps in an unusual way, but it's not an unnatural one. Quite often people have a limited amount of time in which to do the optimization task, and they run the tools for that time and then take the best answer that they've got, and take a view about whether the answer is usable or not. So in a sense, it's fair to say, well, let's run this software for 2 hours or whatever, 4 hours or whatever, and see what the best solution is, and compare the quality of solutions obtained by different technologies. We can summarize these results. If we say on average there, using normal arithmetic average, you can see that ODH CPLEX does rather better than CPLEX on its own. And I should say that CPLEX is a good optimizer. It's one best around. And we're not saying that traditional optimization is bad or that CPLEX is a bad example of it. Quite the contrary, it's a very good example of it. And ODH CPLEX uses CPLEX, of course. But what we are saying is that for these hard models, where you're just running for the time that you've got, and you want the best solution that you can, then perhaps ODH CPLEX represents a better tool than the standard MIP technology. And here we can see how much better it is. If we take the average time to solve those models, it's smaller a little bit using ODH CPLEX, but most importantly, the average gap is quite a lot smaller. It's just a way of sort of characterizing how well you've done after that 2-hour period. If I compare the results we got now with what we had 18 months back, I can tell you that with the 8 threads running on a 4-core workstation, we're now twice as good in the sense that our gap's half what it was before. If we're running on 12 threads on a server, or at least the server that we have, then we were 50% better. So from that last slide then, we can take away that this technology works for getting better solutions to big problems, and that we've managed to improve it over the course of the last 18 months. For the more academically minded, I've looked at the so-called open set of MIP models. These are models whose optimal solution is not known. There's a public collection, and when I looked at it, there were 286 models in it. Solutions were known to 257 of them, but no solution was known to be optimal. And as you can see, by method of subtraction, there were 29 models there to which no feasible solution had ever been found. So I tried out ODH CPLEX on the set towards the end of last year, and essentially gave it 2 hours on each model on various platforms to see how we got on. What happened was that we proved optimality, or at least found solutions which we could prove to be optimal, to zero gap on 13 of the models. And if we were content with the tolerance that's normally used, we could prove the optimality to more than that. And in fact, using the server, using more threads, we did better. We got optimality proven on 16 of the 257 models. We also found, apart from optimal solutions, ones that were better than the best known solutions previously found, to almost half the models known to have a feasible solution. 45%, in fact, when we were using 16 threads. Insofar as the models to which no feasible solution have been found, we found solutions to 5 of them, which is not bad. We're only using, fairly standard hardware that is present in most offices. We were only running the models for 2 hours. Okay. Here is the 10 models on which we perform best, I suppose. If you can say best means in the most improved solution over what was previously known. And you can see that we've got much better solutions than was ever had before, although in many cases they're still not brilliant. I wouldn't say that they were anywhere close to optimal. In the main, they're still a lot better than we had before, except possibly on ARMINE 21. So better solutions to almost 40%, and solutions that were as good as those currently known to further 19%. This is how we got on using 8 threads. Here you can see at the top ones where we've managed to prove optimality. They are in yellow. The breast cancer model, which you can see highlighted in pink there, is an interesting one. And if anyone wants me to talk about dirty solutions, they're kind of important for that model, or avoiding them is important. I suppose I should be more precise about it. And you can see that time to solve is well within the 2-hour limit. So those are models there which were not known to have optimal solutions before, and we found either the same solution or better solutions than we had before, and solutions which we can now show to be optimal. Here's a set of models where previously known solutions were not usable, and I've taken usable in this instance to mean with a gap that was greater than 5%, and where if we apply ODH technology, then we can prove that the gap, or find a solution where we can prove that the gap is less than 5%, and so the solution might be might well be good enough to use. And the gap in many of the instances is quite small there, let's say 0.01% or 1.7%. These are the kind of gaps which might be within the range of error in the data going into a model. So to kind of claim that your gap is maybe 1.5% or something, when you know that the data that goes into your model is only accurate 2 or 3%, is a bit silly. Most users of these very big models tend to be content with solutions that are within a reasonable distance of known optimality. So 5% is normally good enough for them. Going on to those 29 models where no solution was previously known, we found solutions, let's say, to 5 of them. One of them was NEOS problems. We almost got a usable solution there. The other solutions are, well, maybe a bit rough, maybe not. No, we haven't been able to prove any kind of optimality guarantee to them beyond the rather big gaps that you can see displayed there. But at least we found a feasible solution. One of my colleagues at IBM was interested in one of these models, and using a bit more work managed to nearly prove optimality to I think it was the waiter model. Which is kind of it went took a lot longer than 2 hours, of course, but at least that model might now be considered solved. So moving on then, how do 16 threads stack up against using 8 threads in this 2-hour time window? Well, 16 threads does better, and as you can see, we get better solutions to nearly half the models. We match on almost 20%, and within the 2-hour time frame, we didn't get as good solutions to the best known on 35 or 36%. We don't do quite as well using 8 threads, but then that's hardly surprising. Those are the models to which a feasible solution was previously known for the 257. So, concluding then my remarks about this tool and its effectiveness in general, then I would say it's relative to traditional optimization better on the harder to solve models. These are usually large, but not necessarily so. And in fact, it can yield significant benefit on smaller but tough models. By small, I mean models that have maybe less than 50,000 or fewer than 50,000 binary variables. It's relatively better again than traditional MIP when it's run on more threads. By and large, although it's effective using 8 threads on a 4-core workstation, it performs better with 12 or 24 or 96 cores on a workstation. Although I should say that as far as we can tell at the moment, the main performance bottleneck is the bus speed of the machine that you're using. Whether that's important depends on your model. If your model is hard, and we have to go quite deep into the branch and bound tree to find solutions, then we'll be passing a lot of information across the computer's memory bus. And so these models tend to clog up with respect to this bottleneck more quickly than other models where we can often find good solutions at the root or even during pre-solve maybe. So depending on your model, the main bottleneck of bus speed will hit you at a different number of threads. I'm looking at one set of models at the moment where in fact 96 threads are quite a lot better than 48. Your money models, many typical models going beyond say 24 threads is perhaps not very useful. Model specific, but as a general rule, going sort of beyond 24 or 30 threads is not always helpful. It's not usually helpful. At the moment, it's possible that computer design will change, and many companies I know are working on the design of the memory bus. We might well see this particular bottleneck move in the next 2 or 3 years. So I know that Intel are working on it, NVIDIA are working on it, and each company is saying, well, the breakthrough is just around the corner. And one of these days, I guess we'll get there. And there'll be great leap forward then in terms of the size of model that you can reasonably work with. Now, for AIMMS users, ODH CPLEX is just integrated into it, just like CPLEX. We've got easy to use access to ODH's parameters and tolerances, just like CPLEX, and we can use the algebraic structure which you've used for building a model within AIMMS to guide the decomposition process. For some AIMMS customers reporting quite good results. And I think at this point, let's move on to look at how it appears within the AIMMS framework. Okay, I'm not
I can
AIMMS
speak
guru, so
a
I'm
bit
going to
about
hand over at this point to Mohan, who's going to take you through in a more knowledgeable fashion.
Yeah, thank you, Robert. So once your license allows you to use ODH CPLEX, it appears as one more solver in the list of solvers available in AIMMS. And you can set ODH CPLEX as the default solver for different types of problems in the solver configuration window. Or alternatively, you can also use ODH CPLEX as the solver for one particular model in your code, like shown in the presentation there. This is particularly helpful when you have multiple math models in your project and you want to use ODH only on one of those models and use CPLEX or other solvers for the other models based on some tests you might have done, with like ODH CPLEX performs better for one of those hard models, and it's better to use CPLEX for the other models. And all of ODH parameters can also be set through the AIMMS project options tool. You can also set all of these options using AIMMS functionality. Like Robert mentioned, ODH can decompose the AIMMS model automatically, but you can also guide the decomposition process, which variable goes into the main model or the sub problem using AIMMS GMP functions. Robert will now speak about some AIMMS customer cases.
Yes, so we have a customer in the chemical industry who uses ODH, and he gets better solutions to his supply chain models than was possible just using CPLEX. These are models with relatively few binary variables as it happens, and a very significant linear component. So they're not necessarily models that you'd suppose ODH would be good at solving. But nonetheless, to some of his bigger models, he's getting solutions of the quality that he wants, which is in this instance a 2% optimality gap in under 2 hours, whereas with CPLEX on its own, sometimes it has to run for considerably longer, depending on the size of the model, of course. And you can see there some of his results. And as you might expect, for the hard ones, then ODH tends to do relatively better if we measure hardness as the time that CPLEX takes to get to that gap. So when CPLEX doesn't take very long, then ODH finds it hard to beat. But when CPLEX is taking significantly longer, ODH tends to get there relatively more quickly. So he's pleased. And here's a model from another user who also happens to be in the chemical industry, where he's going to a much tighter gap, I think probably to default 0.01%. And even then, ODH CPLEX is managing to get there in significantly less time. Sufficiently less time for it to be worth using, particularly I think he's running on the cloud. I mean, Mohan Ralkis may wish to say something about that later on. So talking about clouds, ODH CPLEX will run on the cloud, and it's kind of useful for some users because if it takes less time to solve, then quite often you're saving directly on your cloud costs. It's not like being able to leave the thing running overnight whilst you go and get some sleep with no extra cost except that of the electricity. When you're using the cloud, sometimes the per unit time cost can be significant. one of our users who's got sort of workforce scheduling models tends to get 90% savings in solve times, in total solve times by using ODH. That obviously reflects straight back on his cloud costs. So it's kind of handy from that perspective, as well as giving you solutions to models that wouldn't otherwise be at all useful. So just concluding then, customers like you want to solve larger and larger models. These are models which are not just pointlessly large, they are models which often contain quite a lot more detail. Particularly when it comes to scheduling models, we can think about looking at much smaller time slots, much finer granularity to use in our scheduling. This tends to be critical for the utility of the models. So these larger models tend to be useful from in a straight production engineering standpoint in the way that the coarser, smaller models would not be. So it's important. The size of these models is important. It's important to the model's utility. We've seen, at least with the subsets of a very big scheduling model, that there can be quite hard barriers to the size of the model that you can reasonably solve using standard optimization technology. The idea of ODH heuristics or ODH CPLEX is to provide solutions, usable solutions, which would otherwise not be available. ODH CPLEX is able to give you some optimality guarantee, and you can run it to some kind of required gap, whereas ODH heuristics used just as its engine just provides solutions. The reason you might not want to have a gap, why you might want just to get good solutions, is that you might know what a good solution is. And when it comes to running this technology, we're running it in parallel with CPLEX. So we're having to share the computer resources. And the more resources you give the tool, the better it does. So ODH heuristics run on its own, just running the engine, will potentially give you better solutions in the particular time frame than you get for running it within CPLEX, in the ODH CPLEX framework, where a lot of those resources had to be handed over to CPLEX, so CPLEX can do its bit. But ODH and CPLEX interact with each other, they communicate. Sometimes CPLEX does things that ODH can't and sends useful information to ODH, things like bounds, new boundaries inferred on variables. ODH in turn sends solutions back to CPLEX, which you can use for tree pruning and generating better cuts. So there's a synchronicity between the two products, which tends to work pretty well. And quite often, ODH CPLEX will in fact give you better solutions than you get just using the engine on its own, despite the fewer resources that are going into ODH heuristics. So ODH CPLEX is, by and large, the tool of choice now for users with wanting to deploy this kind of technology on their models. Parallelization has been the big revolution, I suppose, in computer technology over the last 10 years. And it's where, I suppose, development is proceeding most rapidly. And parallel solution methods are the best way of exploiting this new technology, this new hardware technology. And we try to do that. And I think we're quite successful, although as you've seen, what we can do is currently limited by available memory bus speeds. So, thank you for listening. If you've got models that you think might be suitable for this technology, then we're happy to work with you. You could send us difficult models and we'll tell you whether the technology works and send you the results. Or if you wish, you can request an evaluation copy. The AIMMS people, of course, are in charge of this for ODH running within the AIMMS platform.
Thank you very much, Dr. Ashford. It's time to probably take a few questions. There are a few that have already piled up. Okay. In the interest of time, I will maybe quickly go through a couple of questions, and then others, please do reach out and post your questions, and we will make it a point to at least answer your questions offline if we don't get to them during the webinar here.
All right, I just brought out the Q&A panel here. So I'll just look at the questions I can see. And you know, as I answer these, others may occur to members of the audience. So if we run out of time, then we'll deal with the questions offline. I don't have the times to first feasible and optimal, as opposed to finding optimal solutions to hand, but I would say that on average, ODH does quite a lot better, A, getting an initial feasible solution, and B, getting the optimal solution, although perhaps not being able to prove that it's optimal. Much better, that is, than standard optimization technology. Moving on, so the answer is that the times are better, but I don't have the numbers to hand. I could, I guess, dig them out from the logs and compile tables of results that could be sent round. So that'd be a kind of useful thing to do. Now, the next questioner remarks that we're using parallelization to improve the model running time. It's the the optimization solve time. What about using it to parallelize data preparation? And any of you who've got experience of dealing with these large models knows how time-consuming it can be to do basic things to data. You know, check its consistency and just get it from data sources. The answer to that question is that that's not, unfortunately, our area of expertise, but parallelization of the data prep is something that some people do, and maybe Mohan, you would like to say something about that in respect of AIMMS? Okay, well, we'll leave that for the AIMMS experts to consider. Moving down the list. Yeah, well, we can look at providing information on the dual bound, the so-called best bound, but although it's perhaps not the best way of highlighting the performance of heuristics, it is something, it's a measure that people are kind of used to using. So if one has to say, how good is my solution, if you don't know details of the model, it's the only way I know of kind of characterizing it. You can use ODH from within the concept modeling framework provided by IBM and the iLog. So the answer to that question is yes. As to comparisons with a CP optimizer, we've had a couple of models where we thought, look, it's a scheduling model, why don't we try CP? And the trouble is, it's very hard to compare like with like. So IBM have a tool which takes an ordinary MIP model and turns it into a form suitable for running its CP optimizer. And in those circumstances, in my experience, the CP optimizer didn't do it all well. So that was one comparison that we did, although to be fair, that wasn't a particularly reasonable one from the perspective of a constraint programming expert. Would say, well, you've got to program the search, you've got to present the model in a particular way to get the most out of constraint programming. And I'm sure they're right. So we've no direct comparisons where a CP expert has gone in there and done what I would consider the best possible professional job in formulating the model from a constraint programming perspective. In the rather sort of cavalier comparisons we've done, then ODH turned out a lot better. That perhaps doesn't mean anything except that it's something we've looked at. Yes, we've solved some TSP models. Many scheduling problems look like TSP models, in fact, and so, or have TSP models as a subset. So yes, we've looked at those. Last question is, I've got there is kind of interesting. It says, and I'll read it out, is the problem required to have some special structure? Well, you might think that it would be, because we can't do a kind of useful decomposition if we don't have structure. However, you may recall looking at those slides that some were from the health care sector, and those theatre scheduling models are actually 100% dense. And I did not expect ODH technology to do it all well, but it did. So the answer to that question is that it does seem to work on some models which don't have any structure at all, models that you wouldn't expect, which was kind of good news for me, and it was good, even better news for the user. As to how many threads would be available on the AIMMS Cloud platform, that depends on your particular cloud arrangement, and I'll hand that back to the AIMMS people for a more precise answer. Mohan, are you able to comment on that?
Yes, I saw NSK pressing the button. Would you say anything? Would you like to say anything, NSK?
Oh, no, I was just processing the question. Go ahead. You're the better person.
Okay. Yeah, I can give some details there. By default, every app gets four threads on the AIMMS Cloud platform, and if if we have evidence that a model benefits from more or less threads, we can arrange that. So you can use ODH CPLEX on AIMMS Cloud, and it will start with 4 threads. But like we can make that particular app to work on 8 threads or 12 threads instead.
Okay, well, I think I've covered most of the questions, although 3 of them are still scheduled there as being open, according to the questioner.
That is probably me being slow on the uptake. So,
well, not necessarily. Maybe I wasn't clear. It's true that we could produce some more interesting statistics for how well ODH performs, particularly in respect of getting a feasible solution, getting the optimal solution, or even getting the the solution that it came away with at the end. And on those measures, from the experience I have, I would say that ODH performs better than it does if you look at the straight gap at the end of the time. And I do agree that looking at the gap is perhaps not the best metric to use. And I have already remarked that you can use ODH within concert, and some of our users do. So I think that wraps up those 3 questions there.
Excellent. Thank you very much, Dr. Ashford. I'm going to hand it back to Kara to wrap things up. Thanking everybody who participated with your questions and your attendance. Thank you.
Well, thank you for listening.
Great, thank you, everyone. We appreciate you being here. Like I said, if we didn't get to your questions during the webinar, please note that we'll be in touch via email within the next 48 hours or so. We will be sending out a link with the recording of this webinar, as well as the PDF of the slides within the next week. In the meantime, you can check out our new posts in the AIMMS community, as well as if you would like to try your hand at what you saw today, please email nsk@aimms.com. And we will set you up with a temporary license with these capabilities. If you have any questions for any of us at AIMMS or Optimization Direct, please feel free to reach out to us. Right after this webinar, you will see a survey with a few questions, and we'd really appreciate it if you could take a minute to provide us with some feedback about this webinar. Thank you again for joining us today, and we'll see you next time. Take care.